Welcome Axor Galactic Observatory. Tonight, the journey begins with one of the most haunting questions in all of science. In a galaxy filled with hundreds of billions of stars, countless planets, and more than enough time for civilizations to rise and spread, the universe should be alive with signals, structures, and evidence of intelligence. And yet, when humanity listens, it hears almost nothing, only silence. In this documentary, the story moves through the Fermi paradox, the great filter, and the unsettling possibility that advanced civilizations may vanish before they ever reach the stars. This is not just a question about aliens, it is also a question about survival, about time, and about what may happen to any intelligent species that becomes powerful enough to shape its own destiny. If this kind of deep space mystery fascinates you, please take a moment to like the video, subscribe to the channel, and join Axor Galactic Observatory for more journeys into the dark unknown. The Milky Way extends across space as a broad and quiet system of stars, gas, dust, and dark matter, turning slowly over spans of time that exceed ordinary human thought. Its disk measures roughly 100,000 light-years across, with spiral arms curved around a dense central region where stars gather more closely together. Within that great structure, the Sun moves in a modest orbit far from the center, one star among hundreds of billions. Astronomers estimate that the galaxy contains around 400 billion stars, though the exact number remains uncertain because dust clouds hide many regions from direct view. Even the lower end of these estimates presents a scale so large that it reshapes the imagination. A person counting one star each second would continue long beyond the rise and fall of known civilizations on Earth and still remain far from the end. The Milky Way is not only large, it is also old. Its earlier stars begin forming more than 13 billion years ago, and many stars shining today are billions of years older than the Sun. In that immense span of time, stars are born from cold clouds, planets gather from disks of dust, worlds cool or burn, atmospheres thicken or disappear, and the chemistry of matter continues its slow work in the dark. Seen from this outer scale, the galaxy appears less like a single place and more like a vast archive of separate experiments unfolding at once. Some stars are too massive and live too briefly. Some are faint and stable for extraordinary lengths of time. Around many of them circle planets of rock, ice, or gas. And around some of those planets, the balance of heat may allow liquid water to remain for long periods. Over the last several decades, observations from space telescopes and ground observatories show that planets are common. They are not rare exceptions. They appear to be part of the ordinary outcome of star formation. Rocky worlds also appear common enough that the idea of habitable environments no longer seems remote. The habitable zone, defined simply as the range around a star where surface temperatures may allow liquid water, is not a guarantee of life, but it does describe a condition that nature can produce many times. This matters because it broadens the stage. Instead of one unusual world standing alone in a mostly barren galaxy, the Milky Way begins to look like a place with many possible settings for biology. Water is widespread, carbon is widespread. Simple organic molecules are found in interstellar clouds, comets, and meteorites. The materials of life do not appear confined to Earth. They drift through space, gather into worlds, and endure in cold regions far from starlight, as well as on warmer surfaces closer in. From the outer view, nothing in the broad arrangement of the galaxy suggests that Earth should be the only place where living systems might emerge. On the contrary, the combination of age, scale, and chemical abundance suggests repeated opportunity. Billions of stars older than the Sun have had more time. Many planetary systems have formed, changed, and settled long before Earth existed. If even a small fraction of suitable worlds develop life, and if even a smaller fraction of living worlds produce intelligence and technology, then the galaxy might be expected to contain signs of that long history. Yet, the Milky Way, observed as carefully as modern tools allow, remains outwardly quiet. The silence is not a dramatic silence of complete emptiness, because the galaxy is full of natural sound in the scientific sense. Pulsars sweep out regular radio pulses. Black holes pull in matter that glows in high-energy light. Nebulae radiate, stars flare, planets transit, and gas clouds emit at specific wavelengths. The galaxy is active with natural processes. What is missing is something else. What is missing is any confirmed sign that another technological civilization has marked the sky in a way that stands apart from nature. No verified signal carries the pattern of deliberate transmission from another world. No confirmed structure shows the clear signature of vast engineering built by non-human intelligence. No probe, artifact, or machine of extraterrestrial origin is known within the solar system. The silence is therefore specific. It is the silence of intelligent intention. That absence becomes more striking when placed against the size of the setting. 400 billion stars create room for countless histories. A galaxy older than 13 billion years creates time enough for very slow processes to finish. A civilization does not need to appear everywhere at once to leave some mark. It needs only to arise once in the distant past and endure long enough, or spread slowly enough, for evidence to accumulate. Even modest activity repeated over millions of years can alter the appearance of a region, send signals across long distances, or leave durable traces in stable places. The Milky Way has offered not just one chance for this, but many. Its oldest stars begin shining billions of years before the sun forms. On Earth, life appears relatively early once conditions become stable, and over immense stretches of time simple organisms give way to more complex forms. Intelligence capable of technology arrives very late in Earth's history, but it arrives nonetheless. That single example proves at least one path exists from chemistry to thought. It does not prove the path is common, yet in the wide and ancient context of the galaxy, even uncommon events can become expected if given enough opportunities. This is what lends weight to the quiet. The contradiction does not begin with strange stories or dramatic speculation. It begins with ordinary astronomical facts. The Milky Way is large. The Milky Way is old. Planets are abundant. Some rocky worlds occupy conditions that may allow water to remain liquid. The chemical ingredients associated with life are present across space. Natural history on Earth shows that matter can organize into biology, and biology can, under at least one set of circumstances, become a technological species. None of these facts alone demands company in the galaxy. Together they make company seem plausible. Together they make total absence harder to accept without reflection. From a calm and distant view, the Milky Way should not feel empty in the technological sense. It should feel at least faintly inhabited by traces, by transmissions, by remnants, by some sign that intelligence has taken root elsewhere in all this time. Instead, the sky offers stars, dust, radiation, gravity, motion, and a deep stillness where evidence of other minds has not yet appeared. The galaxy remains a grand natural system that reveals structure everywhere and intention nowhere. In that contrast between abundance and absence, between opportunity and silence, the outer face of the problem takes shape. In the summer of 1950, the setting is not a telescope dome or a formal lecture hall, but a cafeteria at Los Alamos in New Mexico, where a group of physicists walks to lunch under a bright sky. The place still carries the weight of recent history. Only a few years earlier, many of the same minds helped build the first nuclear weapons, turning abstract theory into physical force on a scale the world has never known before. At lunch, however, the conversation moves lightly. A cartoon from the New Yorker circulated, showing aliens stealing trash cans from city streets, and the image gives the group a moment of amusement. Reports of flying saucers are also moving through newspapers at the time, part rumour, part curiosity, part early popular fascination with visitors from elsewhere. The talk drifts between humour and speculation. Then Enrico Fermi, already known for extraordinary intuition and speed of thought, asks a question in a plain and almost casual form. He asks where everybody is. The words are simple. Their effect lasts for decades. Fermi does not need a chalkboard in that moment. He does not need a published paper or a formal audience. The power of the question lies in the fact that so much is already contained inside it. He's not asking whether stories of alien craft are true. He's asking why a galaxy that seems old, rich, and full of opportunity shows no clear sign of other technological beings. Those around him understand that the question is not idle. It follows from arithmetic and timescale. If stars and planets are widespread, and if some of them are far older than the Sun, then intelligent civilizations should have had ample time to emerge long before humanity. If even a few of those civilizations develop technology and continue for long enough, then the galaxy should not appear untouched. Evidence should exist somewhere, either nearby or far away. Fermi compresses all of this into a single sentence that feels conversational and yet carries the weight of a scientific challenge. The question becomes memorable partly because it is so ordinary in form. There is no elaborate wording. No special terminology is required to understand it. A child can grasp the structure of the puzzle. A galaxy with many stars seems like a place where life might arise more than once. A galaxy much older than human civilization seems like a place where others, if they exist, could have started long ago. Yet when humans look outward, no confirmed sign answers back. The strength of the question lies in this contrast between expected abundance and observed absence. The lunch itself becomes part of the story because it shows how a profound scientific problem can emerge from familiar conditions, from a walk, a meal, a joke, a mind turning quietly beneath ordinary conversation. Fermi has a reputation for estimating physical realities with unusual speed. During the first atomic bomb test, he famously drops small pieces of paper and watches how the blast wave moves them, using that simple observation to form a rough estimate of the explosion's power. That same habit of turning reality into rapid calculation is present in the cafeteria question. Though he leaves no formal paper defining the paradox, later recollections from colleagues suggest that he has been considering the number of stars, the probable formation of planets, and the times required for travel or expansion across the galaxy. The contradiction seems plain to him. The Milky Way is ancient. Technological civilizations, if not extremely rare, should have had enough time to spread or at least to become detectable. But the world reveals no clear trace of such activity. The importance of this moment grows after the fact. At the table, the question is brief. In the history of science, it becomes enduring because it is never fully settled. It is later called the Fermi paradox, though it is not a paradox in the strict logical sense. It is more accurately a tension between expectation and observation. The expectation comes from broad astronomical reasoning. The observation is silence. The problem stands at the intersection of astrophysics, biology, probability, engineering, and the long-term behavior of civilizations. What begins as a sentence over lunch becomes a frame through which later generations examine the possibility of life beyond Earth. It also changes tone over time. At first glance, the idea may seem playful, shaped by the cultural atmosphere of sources and stories from the middle of the 20th century. Very quickly, however, it deepens into something more serious. If intelligent life is common, then its absence from observation demands explanation. If intelligent life is rare, then Earth may occupy an unusual position in the galaxy. If civilizations tend to destroy themselves or fade before becoming visible, then the silence may carry implications not just about others, but about humanity itself. The question is therefore not only about alien life, it is also about how long intelligence lasts, how often it becomes technological, how it uses energy, whether it expands, whether it survives, and whether it inevitably leaves marks on the larger environment. Fermi's lunch question matters because it does not allow the subject to remain vague. Before that moment, one may imagine extraterrestrial life as a broad possibility, something to wonder about without structure. After that moment, the issue sharpens. It becomes possible to ask what should be seen if the galaxy hosts many civilizations. It becomes possible to ask whether absence of evidence is still reasonable after billions of years. It becomes possible to look at the sky not only with curiosity, but with expectation. The paradox therefore does not arise from fantasy. It arises from a mismatch between what the size and age of the galaxy seem to permit and what careful observation has not found. The lunch scene remains vivid because it captures the origin of that mismatch in human terms. No monument marks the exact force of the sentence when it is first spoken. No ceremony announces its future influence. A small group shares a meal. A brilliant physicist turns an ordinary discussion toward a larger horizon. From that point forward, the silence of space becomes harder to ignore. It is no longer only a background condition. It becomes an active problem, something that presses against calculation and evidence alike. The history of the paradox often returns to this table, because the simplicity of the setting mirrors the simplicity of the question. The deeper one looks, the stranger that simplicity becomes. In a galaxy with so much time and so many worlds, why does the record of observation remain empty of confirmed company? That quiet sentence from lunch remains in motion, moving outward through decades of astronomy and speculation, never losing its force because the sky has not yet answered it. The age of the Milky Way changes the scale of the problem more than any other single fact. A large galaxy may still remain quiet if it is young, if stars and planets have not had enough time to move from formation toward biology and then toward technology, but the Milky Way is not young. Its earliest stars begin to form more than 13 billion years ago, not long after the universe itself becomes old enough for large structures to gather from cooling matter. Since then, generation after generation of stars has lived and died, enriching interstellar space with heavier elements forged in stellar interiors and scattered outward by winds and explosions. Carbon, oxygen, silicon, iron, and other materials essential for rocky planets and complex chemistry do not appear all at once. They accumulate gradually as stellar history unfolds. This means that the galaxy becomes more capable of producing Earth-like worlds over time. By the time the Sun forms, the Milky Way already holds an immense prior history behind it. The Sun itself is about 4.5 billion years old. In human terms, that age feels almost beyond comprehension, but in galactic terms it places the solar system somewhere after the beginning, not near it. Many stars in the Milky Way are far older. Some have an advantage over the Sun measured not in millions but in billions of years. That difference matters because on Earth, life takes a very long time to move from simple beginnings to technological intelligence. The earliest clear evidence for life appears relatively soon after the young planet cools and stabilizes enough to support liquid water. But for most of Earth's history, life remains microbial or otherwise non-technological. Only after immense biological time do multicellular organisms diversify, complex ecosystems develop, vertebrates spread across land and sea, mammals rise after the decline of non-avian dinosaurs, and one primate lineage eventually learns to shape matter with increasing precision and to study the sky that surrounds it. From the first simple cells to radio telescopes and spacecraft, the path takes roughly 4 billion years. This does not prove that all worlds require so much time, nor does it prove that all worlds follow similar paths. It simply provides one example of how long the process can take even when life begins early. Once that timescale is placed against the age distribution of stars in the Milky Way, the implications become difficult to ignore. A planet orbiting a stable star that forms 2 billion years before the Sun could, if life appears and develops there with roughly comparable speed, produce a technological civilization billions of years before human beings emerge on Earth. A world that begins 5 billion years earlier could possess a margin of time greater than the entire recorded history of life on land here. A civilization with even a small head start in the scale of billions of years would not be merely ahead. It would be ahead by an interval so large that most analogies fail. Between early stone tools and modern science lies only a tiny fragment of geological time. Between a civilization older than humanity by several billion years and humanity itself lies an abyss of duration. This is why the age of stars becomes central to the Fermi paradox. It is not just that other opportunities may exist. It is that many opportunities may have opened long before Earth ever forms. The galaxy does not arrange all possible civilizations on a single starting line. It spreads possible beginnings across deep time. Some stars ignite early, some much later. Some systems lose their planets or remain hostile. Others may settle into long periods of stability. If life requires only suitable conditions and patience, then older stars offer repeated chances for biology to begin and continue. If intelligence is not forbidden by nature, then at least some of those older systems might have reached that stage already. If technology emerges and survives, then the universe has granted it more than enough time to leave marks. The age argument becomes even stronger because the galaxy changes chemically over time in ways that favor planet formation after the earliest eras. The first generations of stars contain mainly hydrogen and helium, with very little of the heavier material needed for rocky surfaces, mineral cycles, and complex planetary interiors. Later generations inherit enriched matter from the deaths of earlier stars. By the time the Sun forms, the ingredients for rocky planets are already common enough that the solar system contains not just one solid world, but several. This suggests that Earth does not arise in a uniquely privileged cosmic moment. It arises after many earlier cycles have already improved the raw materials available for planet building elsewhere. In that sense, the solar system may be ordinary rather than early. It may arrive after much of the galaxy has already had long experience in making worlds. Astronomers also distinguish between different regions of the galaxy when considering long-term habitability. Areas too close to the crowded center may face more frequent supernovae, stronger radiation environments, or more disruptive gravitational encounters. Areas too far out may contain fewer heavy elements. Between these extremes lies a broad region often described as more favorable for stable planetary systems, with the chemistry needed for rocky planets. The Sun occupies part of that middle territory, but it is unlikely to be the only star there. Countless others lie in similar zones, some younger, some older, some perhaps much older. The existence of those older stars in broadly suitable regions deepens the sense that time should have worked elsewhere long before it works here. The Fermi paradox begins to sharpen under this pressure. It is no longer enough to say that life may be hard. It may indeed be hard. it may require rare sequences of events. Yet when those rare sequences are granted hundreds of billions of stars and billions of years, the expectation of at least some success becomes hard to dismiss. Even very unlikely outcomes can become statistically meaningful when the number of trials is vast and the available time immense. The age of the galaxy therefore acts like a multiplier applied to every hopeful estimate. It amplifies opportunity. It stretches the window in which life, intelligence, and technological activity might appear. It allows for slow beginnings, setbacks, extinctions, recoveries, and second attempts. It gives worlds time to cool, oceans time to form, chemistry time to organize, and evolution time to wander through long periods of apparent stillness before arriving somewhere new. The Milky Way does not merely contain stars, it contains ancient stars, old systems, and a depth of history that should, in principle, make biological and technological repetition more plausible, not less. This is why the silence feels so heavy when placed against stellar age. The older the galaxy becomes, the less persuasive simple delay appears as an answer. This sky is not waiting for its first experiments to begin. It has already been running them for longer than the Earth has existed. That fact does not prove that intelligence must be common, but it does mean that when intelligence is imagined elsewhere, it must often be imagined not as younger than humanity, but far older. And if older civilizations have ever existed in numbers beyond the vanishingly small, the galaxy has had time enough for their traces to accumulate. Yet the stars continue to shine with no confirmed sign that any such long history has made itself visible. Planets now appear to be one of the ordinary outcomes of star formation, rather than rare accidents scattered thinly across the galaxy. This change in understanding is recent in scientific terms. For much of human history, other worlds remain matters of philosophy, imagination, or hope, because no direct evidence exists beyond the planets of the solar system. Even after astronomy grows into a precise science, planets around other stars stay hidden, too dim and too close to their parent stars to reveal themselves easily. That begins to change at the end of the 20th century and accelerates in the early 21st, when improved methods allow astronomers to detect worlds far beyond the Sun. Some are found through the slight dimming of starlight when a planet crosses in front of its star. Others are found through the tiny wobble a planet induces in the star's motion. Over time, the results become overwhelming. Planets are not uncommon. They are everywhere. Many stars host families of worlds. Some systems differ sharply from the solar system, with giant planets close to their stars or tightly packed sets of rocky bodies moving in short orbits. Others show arrangements that feel more familiar. In all cases, the main lesson is the same. The galaxy is full of planets. This matters because the question of alien life changes completely once worlds become abundant. A galaxy of stars alone is not enough. Life as it is known requires environments where chemistry can persist, where energy flows through matter, where liquid water may remain stable for long periods, and where complexity can build without being erased too quickly. Planets and moons provide the settings in which those conditions might exist. Once observations reveal that planets are common, the conversation shifts from whether worlds exist to what kinds of worlds they are. Among the most important ideas in this search is the habitable zone, the region around a star where temperatures on a planetary surface may allow liquid water, given suitable atmospheric conditions. The idea is simple, though the reality is more complicated. Too close to a star, and surface water may evaporate or the atmosphere may enter a runaway greenhouse state. Too far away, and water may freeze globally unless other heat sources or atmospheric effects intervene. Between those ranges lies a zone where liquid water is possible, not guaranteed, but physically plausible. Because liquid water is central to all known life, Planets in this region draw immediate interest. Space missions devoted to exoplanet discovery, especially NASA's Kepler mission, show that rocky planets in or near habitable zones are not rare enough to dismiss. Kepler studies more than 150,000 stars and reveals thousands of planet candidates and confirmed worlds, enough to support broader estimates about the galaxy. The exact numbers remain uncertain because detection methods favour some planetary sizes and orbits over others, but a broad picture emerges. A significant fraction of stars host rocky planets, and a meaningful fraction of those planets may lie in ranges where surface temperatures could permit liquid water under the right conditions. Around Sun-like stars, a commonly cited estimate suggests that perhaps 1 in 5 may host a roughly Earth-sized planet in the habitable zone, though different methods and assumptions produce somewhat different values. Around smaller and more numerous red dwarf stars, potentially rocky planets also appear common, though their habitability is more difficult to judge because those stars often flare strongly and may lock one side of a close planet into constant daylight. Even so, when these estimates are extended across the Milky Way, the result is not a handful of promising worlds, but billions. The number does not prove that billions of living planets exist. It simply states that the galaxy contains a great many places where one key condition for life, surface liquid water, may be physically possible. That is already enough to alter the emotional shape of the question. Earth stops appearing as a lonely exception placed in an otherwise empty design. It begins to resemble one member of a broad class of rocky worlds that nature can produce repeatedly. At the same time, astronomers learn to be cautious. The habitable zone is only a first filter. A planet may sit in the right orbital range and still be hostile. It may lack a substantial atmosphere. It may suffer violent radiation. It may have no magnetic field strong enough to protect its surface environment from stellar wind. Its history of impacts may be too severe. Its chemistry may be unbalanced. Its water may be trapped beneath ice or lost to space. Habitability is therefore not a simple label, but a layered problem. Still, the existence of so many potentially suitable worlds matters because it expands the number of trials available to nature. Even if only a small fraction of habitable zone planets remain stable for long enough, the underlying population is vast. The Milky Way does not offer one favourable setting, it offers many. This abundance also has a temporal dimension. Different stars form at different times, and planets around them begin their histories on different clocks. Some worlds may still be hot and violent, others may have cooled long ago and remained stable for billions of years. If life depends not only on suitable conditions but on long continuity, then the age of some planetary systems becomes as important as their distance from a star. A rocky world around an older stable star may have had more time than Earth has ever known. Such a world may have passed through oceans, climates, extinctions, recoveries, and perhaps biological innovations while Earth was still dust in a forming disk around the young sun. Again, none of this proves that life appears often. It does show that the opportunity for life is not limited to one narrow corner of the galaxy. The diversity of exoplanets also teaches another lesson. Earth may not represent the only possible kind of living world. Some planets may be slightly larger, with thicker atmospheres and deeper oceans. Some may orbit dimmer stars under reddish light. Some may exist as moons around giant planets, warmed by tidal forces in addition to starlight. Within the solar system itself, moons such as Europa and Enceladus suggest that liquid water may also survive beneath ice shells, driven by internal heating rather than direct sunlight. This broadens the concept of potentially habitable environments beyond simple Earth-like surfaces. It becomes possible that the galaxy contains not just many Earth analogues, but many environments where life could persist by unfamiliar routes. The result is a widening circle of possibility. As observations improve, the number of candidate worlds grows, not shrinks. The silence of space therefore becomes harder to place on a shortage of settings. There may still be profound barriers between a habitable world and a living one, between living chemistry and intelligent technology, between intelligence and detectable civilization. But the basic planetary stage now appears common enough that the absence of evidence cannot easily be blamed on a lack of worlds. The galaxy provides many surfaces, many atmospheres, many oceans, many long calendars of time. It provides many places where water may flow, freeze, or cycle through air and stone. In that abundance, the question changes again. The problem is no longer whether the Milky Way has places for life to begin. The problem is why a galaxy that seems so prepared with possible worlds remains so quiet when listened to, with the hope that one of them has already crossed the threshold into visible intelligence. The materials associated with life are not confined to Earth, and this is one of the quiet but important facts that gives weight to the larger question. Long before any organism appears on this planet, the universe is already making the ingredients from which living systems later draw their structure. Hydrogen and helium dominate the early cosmos, but inside stars new elements are formed through fusion. In the deaths of stars, especially in supernova explosions and in the outflows from giant stars, those heavier elements are released into space and mixed into new clouds of gas and dust. Carbon, oxygen, nitrogen, phosphorus, sulfur, iron, silicon, magnesium, and many others become part of the interstellar medium from which later stars and planets form. By the time rocky worlds appear in mature galaxies, the raw matter for chemistry is no longer scarce. It is present in dust grains, frozen coatings, gas clouds, meteorites, comets, and planetary crusts. The Milky Way does not merely contain stars and planets. It contains a widely distributed chemical inheritance shaped by earlier generations of stars. This matters because life on Earth is not built from exotic substances. It is built from common cosmic elements arranged in unusual ways. Carbon forms versatile bonds and allows long chains and complex branching structures. Water acts as a solvent and helps move molecules, moderate temperature, and support reactions. Nitrogen enters amino acids and nucleic components. Phosphorus helps form the backbone of genetic molecules and supports energy transfer inside cells. Metals and minerals participate in catalytic processes and in the structure of planets that regulate atmosphere and surface conditions. None of these ingredients appears unique to Earth. What appears rare, if it is rare, would lie not in the existence of the building blocks, but in the path by which those blocks become self-organizing systems capable of metabolism, replication, and evolution. Observations over the last decades reinforce the idea that prebiotic chemistry, meaning chemistry that may precede life, is not difficult for nature to begin. Astronomers detect organic molecules in interstellar clouds, including simple alcohols, aldehydes, nitriles, and more complex carbon-bearing compounds. These molecules form in cold environments where dust grains act as surfaces on which atoms settle, combine, and are later released by radiation or warming. Comets preserve ices and organics from the early solar system. Meteorites that fall to Earth carry amino acids and a variety of carbon compounds. Laboratory studies and space observations together suggest that complex chemistry emerges naturally when carbon, water, energy, and time are present. This does not mean that life is inevitable. It means that the first steps toward chemical complexity may be common. The distinction is essential. There is a great distance between molecules and cells, between a cloud rich in organics and a system capable of Darwinian evolution. Still, if the galaxy repeatedly creates environments where organic chemistry flourishes, then one of the foundations of the Fermi paradox strengthens. The absence of confirmed alien intelligence becomes harder to attribute to a total lack of relevant matter. Earth itself offers clues, though not final answers, about the transition from chemistry to life. The oldest direct evidence of life is ancient, dating back well over 3 billion years, and some indirect indications may point even earlier, though such evidence remains debated. What seems broadly accepted is that life appears relatively soon after Earth becomes stable enough to support long-lived bodies of liquid water. The young planet is violent at first, with heavy impacts, volcanic activity, and an atmosphere very different from the present one. Even within that harsh early setting, conditions eventually allow oceans, minerals, dissolved chemicals, heat gradients, and repeated cycles of concentration and reaction. Somewhere in such environments, non-living chemistry crosses into self-sustaining biological organization. Scientists continue to study several possible settings for this transition. Some focus on hydrothermal vents in the ocean, where mineral-rich water rises through cracks in the crust and creates steep chemical gradients. Others study shallow pools, tidal flats, volcanic regions, or porous mineral structures that might concentrate molecules and encourage repeated reactions. There is still no final answer about the origin of life on Earth. Yet the speed with which life appears once stable conditions exist has often been taken as a suggestive fact. It may indicate that under suitable conditions, the step from chemistry to primitive biology is not astronomically unlikely. It may also be a misleading impression drawn from a sample of one, because observers can only arise on worlds where that step happens. Both interpretations remain possible. The chemistry itself broadens the puzzle in a calm but relentless way. Water is among the most common molecules in the universe. It is present in interstellar clouds, on comets, in icy moons, in planetary minerals, and in the outer regions of many young planetary systems. Carbon chemistry is widespread. Energy sources are diverse. Starlight drives surface reactions. Radioactive decay warms interiors. Tidal forces knead moons. Impacts, lightning, ultraviolet radiation, and geothermal heat all provide ways to rearrange matter. The galaxy therefore offers not one recipe but many chemical settings in which increasing complexity might arise. Even if most of those settings fail, the sheer number of them suggests repeated attempts over cosmic time. A quiet implication follows. If the ingredients of life are common, then a total absence of life would be surprising. If life itself then appears frequently but rarely advances toward intelligence, the silence would point toward a later barrier. If life appears only rarely despite common ingredients, then the great mystery moves inward to the origin of biology itself. Either way, chemistry is not the place where the problem seems easiest to solve through absence alone. It seems too widespread, too productive, too ready to form complex structures under many conditions. This is why researchers often speak carefully of habitability and biosignatures rather than jumping straight to intelligence. The path may be long. Many worlds may host chemistry without biology, or biology without complexity, or complexity without minds that build instruments. But the farther outward one begins, at the level of atoms, molecules, ices, minerals, and planetary environments, the less empty the galaxy appears. It looks active, fertile in a chemical sense, full of matter that does not remain simple when energy moves through it. Dust grains gather frozen layers. Sunlight breaks bonds and allows new ones to form. Water circulates through rock. Carbon enters chains and rings. Minerals provide surfaces and compartments. Everywhere known science looks, matter seems willing to explore structure. Life may still require rare thresholds beyond this point, but the chemistry of the Milky Way does not feel sparse or hostile to possibility. It feels rich, layered, and patient. The deeper the chemical foundation extends across space, the less satisfactory it becomes to imagine that the silence of the sky begins with a shortage of ingredients. The ingredients are present, the reactions are possible, the environments are many. The unanswered question is whether those ingredients, given enough time and suitable conditions, usually stop at complexity or sometimes continue into the long biological histories that might eventually produce another civilization capable of looking back into the dark and wondering why it hears so little from the rest of the galaxy. In 1961, at the Green Bank Observatory in West Virginia, the question of alien civilizations receives a framework that gives it lasting structure. The astronomer Frank Drake is organizing a meeting on the scientific search for extraterrestrial intelligence, and he needs a way to guide discussion among researchers coming from different backgrounds. Rather than offering a final answer, he writes an equation that breaks the larger problem into a chain of smaller terms. Each term represents one stage in the path from the formation of stars to the existence of a civilization capable of sending a signal that another civilization might detect. The equation does not solve the mystery. Its power lies in making the mystery more precise. Instead of asking in a general way whether humanity is alone, it becomes possible to ask how often stars form, how often they have planets, how many of those planets may support life, how often life appears, how often intelligence develops, how often intelligence becomes technological, and how long such a civilization remains detectable. The value of the framework lies not in exact calculation, because several of the terms remain deeply uncertain, but in the clarity it brings to the shape of the question. The first term concerns the rate at which stars form in the Milky Way. This is one of the better-known parts of the equation, because astronomers can estimate it from observations of gas, young stars, and galactic structure. The exact value varies with method and time, but the galaxy appears to produce roughly one to a few new stars each year. On its own, this does not say much about life, but it establishes the pace at which fresh systems enter the galaxy's long history. Over billions of years, even a modest annual rate leads to an immense total number of stars. The second term asks what fraction of these stars form planetary systems. Here, modern astronomy transforms the discussion. When Drake first writes the equation, no exoplanets have yet been confirmed. In later decades, discoveries show that planets are extremely common, and the fraction of stars with planets appears to be high, perhaps close to unity. This means the second step in the chain no longer looks like a severe bottleneck. Nature does not produce stars and only occasionally add planets. It seems to produce planets as part of the ordinary story. The third term asks how many planets in each system might offer conditions compatible with life. This is harder to define because life may tolerate more environments than those found on Earth. Yet even under conservative assumptions, rocky planets in habitable zones and perhaps some ocean-bearing moons provide a real and significant population of candidates. The first three terms together establish the broad stage. They say, in effect, that the galaxy contains many stars, many planets, and many environments where liquid water and complex chemistry might exist. After that, the equation moves inward toward greater uncertainty. The fourth term asks what fraction of suitable worlds actually develop life. Here the confidence of astronomy gives way to the humility of biology. Humanity has only one confirmed example of life arising, which is Earth. That example is precious, but it cannot by itself determine how frequent life is elsewhere. One interpretation of Earth's history suggests that life appears relatively quickly once conditions stabilize, and this may imply that the emergence of simple biology is not extraordinarily rare. Another interpretation warns that a sample of one cannot support strong conclusions. Observers necessarily find themselves on a world where life begins, because there can be no observers on worlds where it never does. The fifth term asks what fraction of life-bearing worlds develop intelligence. Earth again offers a single and therefore limited example. Life thrives on this planet for billions of years before a species appears that can build radio telescopes or ask mathematical questions about its place in the universe. This suggests that intelligence may not be an inevitable result of evolution. Evolution favours success in local conditions, not foresight, not technology, and not abstract thought for its own sake. Many organisms thrive without anything resembling human cognition. Intelligence may be useful in some environments, but it may also be rare, unstable, or only one among many viable strategies. The sixth term narrows further. It asks what fraction of intelligent species develop detectable technology. Even on Earth, anatomically modern humans exist for a long time before industrial science, electronics, and radio transmission appear. A world may host intelligent beings that never create large-scale engineering or long-range communication. They may remain local, or their technologies may differ in ways not easily detected from afar. By this point in the equation, the chain has already passed through several filters, each one narrowing the number of civilizations that may become visible to others. Then comes the seventh term, the one that gives the equation much of its emotional force. It asks how long a communicative civilization remains detectable. A civilization that develops radio for a brief period and then stops, whether through collapse, transformation, or a shift to harder-to-detect communication methods, contributes only a short flash in cosmic time. A civilization that remains detectable for thousands or millions of years contributes far more strongly. This final term acts like a magnifier. If civilizations are long-lived, then even a modest rate of emergence can fill the galaxy with overlapping eras of detectable activity. If civilizations are short-lived, then even if many arise, most may never coincide in time. The sky can remain quiet not because intelligence never appears, but because it vanishes, changes, or hides too quickly. The Drake equation therefore changes the nature of the Fermi paradox. It does not remove the mystery. It shows where the mystery is allowed to live. Some terms now seem generous. Stars are common, planets are common. Potentially habitable worlds are numerous enough to sustain serious expectation. Other terms remain uncertain in deep ways. Life may be easy or difficult. Intelligence may be frequent or uncommon. Detectable technology may be brief or lasting. The equation permits optimism and pessimism alike, depending on how these uncertain values are chosen. Early discussions often use hopeful estimates and imagine a crowded galaxy rich with communicative civilizations. Later reflection, especially under the pressure of silence, tends to focus on the more fragile terms. Perhaps life is rare after all. Perhaps intelligence is an unlikely branch. Perhaps technological societies are unstable. Perhaps detectability is brief. The value of the equation lies not in a numeric answer, but in this discipline of thought. It prevents the mind from treating the question as one simple step. It reveals a ladder of conditions, each one real, each one uncertain, each one capable of narrowing the field. In doing so, it prepares the way for a more unsettling realization. If the early astronomical terms are not especially restrictive, then the explanation for silence may lie deeper in the chain, in biology, intelligence, technology, or survival. The framework, therefore, does not soften the paradox, it sharpens it, by separating abundance from rarity and potential from persistence. It turns the broad silence of space into a set of narrower and more difficult unknowns. Among all the terms in Drake's framework, the most sensitive is the last one, because it governs not how often civilizations begin, but how long they remain part of the observable galaxy. A civilization may arise on a world after billions of years of chemical and biological history, pass through a brief technical age, and then vanish or change before any distant observer has the chance to notice it. If that detectable phase lasts only a short time, then even a galaxy that produces intelligence many times may still appear empty when examined at a single moment. This is the quiet force of the survival variable. It acts less like one term among equals and more like a gate that can amplify or erase all the others. If civilizations endure for millions of years while continuing to release detectable signals or build visible structures, then even a modest number of origins would fill the Milky Way with signs of intelligence. If they last for only a few centuries in a detectable state, then the same galaxy may contain many extinct beginnings and yet offer almost no overlap between them. The difference between those outcomes is not small, it is enormous. On Earth, the window of detectability is surprisingly young. Radio transmission becomes part of human civilization only in the late 19th and early 20th centuries. In astronomical terms, that is not a blink but something even briefer, an interval so short that it scarcely registers against geological time. For most of Earth's history, life is present but silent in any technological sense. Even for most of human history, intelligence exists without industry, without radio, without spacecraft, without the ability to make a planet visible to distant listeners. This means that one confirmed example of technological life currently provides only a very narrow detectable span. Humanity may continue through this stage for thousands or millions of years, but that remains unknown. It may shift toward communication methods that leak less energy into space. It may reorganize its technologies around local networks, directed beams, or forms of computation that are not easily seen from afar. It may endure and become less visible. It may not endure at all. The survival variable therefore includes more than literal extinction. It also includes transformation. A civilization can disappear from the observational record without disappearing in fact. Still, from the viewpoint of another distant society, the practical result is the same. It is absent. This helps explain why the final term is so disturbing. It invites a possibility that touches not only hypothetical alien worlds, but the future of human beings. If the galaxy is quiet because civilizations do not remain detectable for long, then the silence may reflect a pattern rather than a coincidence. It may suggest that intelligence often reaches a threshold where new powers outpace stability. On Earth, the technical age rapidly produces tools of extraordinary reach. Industrialization changes atmosphere, ocean chemistry, land use, and biodiversity. Nuclear weapons create the ability to destroy cities and threaten global systems within a very short period of time. Biological research offers deep understanding of life but also new forms of risk. Artificial systems increasingly shape infrastructure, communication, and decision-making. None of these developments guarantees collapse, but together they show how quickly a technological species can acquire the means to alter its own conditions of survival. The transition from simple tools to planetary consequence happens in a short span. If such compression is common, then many civilizations may pass through a dangerous interval in which intelligence gives them power before it gives them wisdom, coordination, or restraint. The problem does not need to end in dramatic self-destruction. Long survival can fail through slower mechanisms. A civilization may exhaust key resources, damage ecological systems, or settle into rigid structures that cannot adapt to changing conditions. It may become vulnerable to impacts, nearby stellar events, pandemics, or internal fragmentation. It may divide into isolated populations that lose the capacity for large collective projects. It may choose inward stability over outward expression. It may persist biologically while ceasing to broadcast, explore, or build at scales visible across interstellar space. Yet the central point remains. A short detectable lifespan can make a populated galaxy seem empty. Two civilizations may exist in the same galaxy and still never know of each other if their visible intervals do not overlap. One may flourish and fade millions of years before the other invents astronomy. This possibility softens one part of the paradox while darkening another. It means that silence need not imply total solitude, but it also means that intelligence may rarely hold its form for long. Early optimism around extraterrestrial life often assumes that once a civilization becomes advanced, duration follows naturally. The survival variable challenges that assumption. Advancement may generate fragility along with power. Greater energy use means greater dependency on stable systems. Greater technical sophistication may concentrate risk. Wider reach may create wider consequences from error. Even success can alter detectability. A society that becomes more efficient may waste less energy and therefore shine less brightly in radio or infrared surveys. A society that spreads into digital environments or closed habitats may leave fewer obvious signatures than expected. For an external observer, long-lived civilization and long-lived visibility are not necessarily the same. This is why the survival term exerts so much influence over the whole discussion. Suppose life is fairly common, intelligence uncommon but not exceptional, and technology arises on a modest fraction of intelligent worlds. Those assumptions could still lead to a nearly silent sky if detectable phases are brief. 1,000 civilizations spread across 13 billion years may not overlap often enough to notice one another. Even 1,000,000 civilizations, if they flare for only a few centuries and remain separated across immense distances, may leave less simultaneous evidence than the intuition suggests. Cosmic time dilutes coincidence. The galaxy can contain many stories and still reveal almost none of them in the present. Yet the term remains unsettling because it invites a mirror. The same arithmetic that explains alien silence asks an implicit question about human duration. If civilization on Earth has only recently become visible by technical means, then humanity is not yet evidence of long success. It is evidence of a beginning. No observation currently shows whether this beginning belongs to a stable arc or a temporary one. In that sense, the survival variable is not merely a component of a scientific equation. It is a measure of how often intelligence manages to outlive its own dangerous adolescence, how often curiosity remains joined to continuity, and how often a species capable of measuring stars also learns to persist among them. The silence of space may therefore depend less on whether minds appear and more on whether they last in forms that other minds can detect. If that is true, then the absence of signals does not point first to barren chemistry or empty planets. It points to the fragile duration of visibility itself, a narrow window that may close more often than it remains open. If the question moves away from signals and turns instead toward movement, the shape of the paradox becomes more severe. A civilization does not need to speak across the galaxy in order to become visible. It does not need to send radio messages in all directions or build impossible engines that outrun light. It only needs to spread, slowly and steadily, from one star system to the next over very long periods of time. Once the problem is framed this way, the great distances between stars remain formidable, but they no longer appear decisive. The nearest stars lie several light-years away, and no present human technology can cross those distances quickly. Yet the galaxy is not judged on human lifetimes. It is judged on millions and billions of years. Over such spans, even modest expansion can accumulate into an enormous reach. A society that develops durable spacecraft, long planning horizons, and the ability to use local materials in new systems does not need speed beyond known physics. It needs patience, continuity, and repetition. This is why the expansion argument presses so heavily against the silence of the Milky Way. Consider a civilization that reaches one nearby star every few thousand years, an interval that sounds extremely slow from a human point of view. If it settles or establishes a lasting outpost there, that new site may eventually launch its own missions to nearby stars. The process then ceases to be linear. It becomes branching. One settlement becomes two become four, and so on. Though real conditions would be irregular and shaped by local geography, stellar spacing, failures, and long pauses, even with all those complications, the important fact remains that expansion through a network of stars need not proceed from one original world alone. Each new foothold can become a fresh starting point. Over deep time, this turns limited travel speed into broad spatial reach. The distances do not vanish. They are simply given enough time to be crossed in stages. In this view, the Milky Way resembles an archipelago more than an empty ocean. The islands are far apart, but not beyond approach if voyages can be attempted repeatedly over spans far longer than the life of any one generation. Human history offers much smaller analogies. Seafaring peoples settle islands step by step, often without seeing the full map of the ocean around them. Migration follows coastlines, river valleys, and chains of reachable places. No single journey must cover everything. Instead, the pattern emerges from successive arrivals. Interstellar space would of course be harsher, slower, and more technically demanding, yet the logic of gradual spread remains intact. If a civilization can survive in closed environments, build machines that last, and extract useful material from asteroids, moons, or other planetary bodies, then it may not need perfect Earth-like destinations at every step. Habitats can travel, resources can be gathered, settlements can exist in places that are not naturally comfortable. Expansion therefore depends not only on finding ideal planets, but on the flexibility of technology. This matters because the time available is so great. A few million years sounds enormous on Earth. In the context of the Milky Way, it is a small fraction of galactic history. A civilization that begins billions of years before humanity would have more than enough time, even under very conservative assumptions, to spread across a significant portion of the galaxy. It would not need to do so quickly. It would only need not to stop. This is what makes the paradox feel more concrete under the expansion view. Signals may be missed. Civilizations may choose silence. Communication methods may become subtle or brief. But physical presence has different consequences. Settlements, industry, and long-lived infrastructure alter environments. Energy use leaves heat. Mining leaves changed surfaces. Traffic through systems leaves debris, structures, or artificial concentrations of material. Even if direct contact never occurs, a civilization that spreads widely over millions of years might be expected to leave durable traces visible to sufficiently advanced observers. That expectation grows stronger the older the civilization becomes and the larger the fraction of the galaxy it reaches. Once expansion is treated as a physical process rather than a dramatic fantasy, another feature becomes important. A civilization need not be unified in purpose for spread to occur. It does not require every member to agree. On Earth, migration, trade, exploration, conflict, exile, curiosity, and accident all move populations. Similar motives, or entirely different ones, could apply elsewhere. One group might seek scientific knowledge, another might seek resources, another might leave because its homeworld changes or because it simply can. Expansion can arise from many causes, which makes it harder to dismiss by assuming all civilizations remain content on one world forever. A single society may contain many impulses at once, and over long time even one persistent branch can extend outward. This weakens the idea that alien civilizations might universally choose not to move beyond their origins. It is possible that some would remain local. It is harder to see why all would do so across billions of years. The outer geography of the galaxy also supports gradual spread. Stars are not evenly separated by impossible chasms. They occupy neighborhoods, clusters, spiral arms, and local regions where the next step is sometimes within a few light years. The Sun itself resides in such a region, surrounded by nearby stars that could, in principle, be reached by sufficiently advanced robotic craft traveling well below the speed of light. If that is true here, it is likely true in many other parts of the galaxy. The Milky Way provides many routes, even if no route is easy. This line of thought does not prove that expansion must happen. Civilizations may collapse before attempting it. They may lose interest. They may turn inward. They may change into forms that do not spread materially. Yet the expansion argument shows why distance alone is not a full answer. Distance makes interstellar life difficult. It does not make it impossible on the timescales available. And if even one civilization somewhere in the ancient history of the Milky Way combines durability with a moderate outward impulse, then the consequences should have had time to propagate widely. The galaxy should by now contain not only untouched systems but also altered ones, or at least regions carrying signs of earlier passage. The fact that no confirmed evidence of such spread has yet appeared keeps the paradox in place. The sky still looks natural. The stars still shine without verified marks of an old and patient wave moving between them. When viewed through the lens of expansion, the silence becomes less about whether others can speak to humanity now, and more about why nobody seems to have crossed the vast but conquerable distances over the immense durations the galaxy has offered. That question turns the calm grandeur of interstellar space into something more unsettling. It suggests that the obstacle may not lie in the emptiness between stars, but in what happens to civilizations before they travel far enough to leave unmistakable marks behind them. A more concentrated version of the expansion argument appears when the moving agents are not biological settlers but machines. This idea removes many of the limits that make interstellar travel feel implausible to human intuition. Biological bodies are fragile, dependent on atmosphere, water, radiation shielding, food, sleep, and narrow temperature ranges. Machines can be built for vacuum, cold, delay, and repetition. They do not need comfort. They do not need return journeys. They do not need even to preserve a living crew across centuries. Once that is recognized, the path from one star to many no longer depends on transporting entire civilizations in the human sense. It may depend only on launching durable robotic systems able to travel, arrive, use local materials, and continue the process. This is the logic behind the idea of self-replicating probes, sometimes called von Neumann probes, after the mathematician John von Neumann, who studies systems capable of reproduction in principle, in the interstellar setting. The concept is simple in outline, even if difficult in practice. A civilization sends a probe to a nearby star. After arrival, that probe surveys local resources, mines suitable material from asteroids or moons, manufactures copies of itself or specialized daughter machines, and sends those onward to additional stars. Each new arrival repeats the process. No faster than light travel is required. No magical source of energy is required. The only true requirements are advanced automation, reliable engineering, access to raw material, and enough time. Time, in the Milky Way, is abundant beyond ordinary measure. The distances between stars remain large, but when probes travel at some modest fraction of light speed, the travel times become long rather than impossible. 10% of light speed would carry a machine to the nearest stars in a few decades. 1% would make the same trip last a few centuries. Even 1,000 years between departures or between full replication cycles would remain negligible when placed against millions of years. What matters is not the speed of a single journey, but the cumulative behavior of a branching network. Once probes begin to reproduce across multiple systems, the process becomes expansive in the mathematical sense. Growth may slow in sparse regions and accelerate in dense ones. Some missions may fail, some target systems may lack useful resources, some machines may drift or malfunction. Yet a replication process does not need perfection to transform the galaxy. It only needs enough success for the wave to keep moving outward. This is why the probe argument intensifies the Fermi paradox. It strips away many familiar excuses. A civilization does not need to commit its population to migration. It does not need to expose living beings to radiation, isolation, or centuries of confinement. It does not need to maintain political unity over interstellar distances. It may only need to build a class of machines once, and allow those machines to continue under general rules. Such probes could perform many tasks. Some might explore and return information. Some might seed archives. Some might build telescopes or listening stations around other stars. Some might simply mark presence by durable artifacts placed in stable orbits or on airless surfaces. Others might begin resource extraction, construction, or even prepare environments for later arrivals. In each case, the galaxy would gradually acquire artificial traces. These traces would not need to be dramatic across every system. A sparse but persistent network would be enough. Over a few million years, even conservative models show that a self-replicating wave could spread through much or all of the Milky Way. A few million years is an immense period by historical standards, and an almost trivial one by galactic standards. If a technological species appears even once during the long early history of the galaxy, and chooses, or merely allows, this form of expansion, then by now its artifacts should in principle be widespread. This does not mean every star would host busy machinery. Some systems would be skipped, others would be visited only briefly. Yet the larger expectation would remain. There should be evidence somewhere, perhaps on moons, in asteroid belts, in stable gravitational locations, or in unusual patterns of matter and energy around stars. The solar system itself offers many places where such artifacts could persist for long periods. The moon preserves surface records because it lacks weather and flowing water. Certain orbital regions are dynamically stable. Asteroids drift slowly and contain usable metals and volatiles. If probes had visited during the deep past, they might have left remnants in places where erosion is minimal. No confirmed evidence of such remnants has been found. That absence is not absolute proof of non-existence, because searches are incomplete and many regions remain poorly examined. Still, the lack of clear artifacts matters. The more plausible machine expansion appears, the more striking the absence becomes. Another unsettling feature of the probe scenario is that it does not require a civilization to remain alive after launch. A society could vanish, and its machines could continue for millions of years. The visible footprint would outlast the builders. This means the silence cannot easily be explained by assuming all civilizations perish young. Even short-lived species might still fill the galaxy with their tools if they reach sufficient technical maturity before decline. A civilization could fail and yet remain cosmically present through autonomous systems. If that has never happened, then perhaps the threshold is harder to reach than it seems. Perhaps reliable self-replication in uncontrolled environments proves nearly impossible. Perhaps advanced societies avoid creating such systems out of caution. Perhaps machines decay too quickly or turn inward rather than outward. Each of these responses is possible, but each restores complexity to a problem that the probe idea first simplifies. The simplicity is the reason the argument remains powerful. It asks very little compared with the imaginative visions often associated with interstellar civilization. It asks only for engineering extended over time. It asks only whether intelligence, once capable of building self-maintaining machines, tends eventually to send them outward. If the answer is yes, even once, then the natural expectation is a galaxy with traces. If the answer is no in every case, then another question emerges. Why not? What universal barrier prevents it? Is the barrier technical, ethical, ecological, or existential? The probe concept therefore shifts the Fermi paradox from dreams of crude starships to a colder and more practical logic. Machines are enough. Delay is acceptable. Repetition does the rest. In a galaxy older than 13 billion years, that logic should have had more than enough time to operate. Yet the stars remain free of confirmed alien machinery. The moon remains silent. The asteroids show no clear marks of ancient industry, and the wider sky offers no settled sign that automatic explorers have passed before. The quiet that follows is not the quiet of an untouched wilderness alone. It is also the quiet of a place where even the simplest durable strategy for galactic presence appears, so far not to have happened in any way that observation can confirm. Humanity has not remained passive before the silence. For more than 60 years, astronomers and engineers have used instruments of increasing sensitivity to search for signals or traces that might indicate technological activity beyond Earth. This effort is often grouped under the name Search for Extraterrestrial Intelligence, or SETI. Though the methods vary across time and technology, the central idea is simple: a civilization using high-power radio, directed light, or other forms of communication might create patterns that differ from natural astrophysical sources. Those patterns could include narrow bands of radio emission, repeated pulses, mathematically structured sequences, or signals concentrated at frequencies that stand out against cosmic background noise. In principle, a technological source might be easier to recognize than a biological one because it could impose order on energy in a way nature rarely does. The challenge is that the sky is large, frequencies are many, time is continuous, and any signal may be brief, directional, weak, or unlike current human expectations. Even so, the search has steadily widened and deepened. One of the first focused efforts begins in 1960, when Frank Drake points the radio telescope at Green Bank toward two nearby sun-like stars and listens near the hydrogen line. A naturally important radio frequency often imagined as a sensible place for interstellar communication. He hears nothing that can be confirmed as artificial. That result in itself is not surprising. The search is tiny compared with the galaxy. Yet the importance of the effort lies in the beginning of method. It replaces abstract speculation with targeted observation. Over the following decades, radio astronomy grows more powerful, receivers become more sensitive, data processing improves, and the search expands beyond a handful of stars and frequencies. Large telescopes scan broader regions of the sky. Programs look for narrow-band emissions because natural astrophysical processes usually spread energy across wider frequency ranges, while intentional transmission might concentrate it tightly. Researchers also search for repeating patterns, regular pulses, and anomalies that persist under repeated observation. Again and again, candidates appear and then fade under scrutiny, resolving into interference, instrumental effects, satellites, aircraft, or natural phenomena that at first seem unusual. The most famous case arrives in 1977, when the Big Ear radio telescope at Ohio State records a strong narrowband signal from the direction of Sagittarius. Astronomer Jerry Amon circles the printed output and writes one word in the margin that later gives the event its name. The signal lasts 72 seconds, consistent with the way the fixed telescope sweeps the sky as Earth rotates. Its frequency lies near the hydrogen line, and for a brief moment it seems to possess several of the qualities expected from an artificial source. Yet it never repeats. Follow-up observations over many years fail to recover it. Without repetition or independent confirmation, the signal remains unresolved. It becomes a symbol of the search itself, balance between hope and frustration. It may have been natural, instrumental, or something still poorly understood, but it does not become proof of alien technology. The wider story remains one of increasing effort and continued absence. SETI does not stop with isolated observations. Institutional projects, privately funded surveys, and international collaborations continue to scan the sky. Arrays of radio dishes listen across wide frequency ranges. Optical searches look for brief laser pulses that might outshine a star for an instant in a narrow beam. More recent efforts also use advanced computing to process enormous data streams, identify unusual patterns, and distinguish cosmic signals from the dense fog of human-made radio noise that now surrounds Earth. Breakthrough Listen, one of the most ambitious modern programs, greatly expands the scale of the search by surveying nearby stars, the galactic plane, and even nearby galaxies with some of the most capable radio telescopes in operation. The amount of data collected in these efforts dwarfs what earlier generations could manage. Yet the central result remains the same. No signal has achieved the standard of confirmed extraterrestrial intelligence. This repeated null result can be misunderstood. It does not mean the sky has been searched completely. Far from it. The search space is immense beyond ordinary intuition. It includes position on the sky, frequency, bandwidth, signal type, polarization, repetition rate, time, strength, and directionality. A civilization may transmit rarely, in beams not aimed at Earth, using methods humans do not prioritize, or in wavelengths not yet surveyed deeply enough. A silence in the searched region does not prove silence everywhere. SETI researchers often compare the examined portion of the full search space to a tiny amount of water drawn from an ocean. This caution is important and scientifically honest. At the same time, the expanding scale of the search still matters. Each generation covers more stars, more frequencies, more observing time, and more kinds of signal. The absence of detections is therefore not meaningless. It slowly constrains certain expectations. It suggests that the nearest stars are not broadcasting powerful continuous beacons directly at Earth, in the frequency ranges most commonly explored. It suggests that obvious galaxy-wide radio activity is not filling the sky. It suggests that if technological civilizations exist, they may be rarer, quieter, more short-lived, less interested in broadcasting, or technologically different from the simpler models often imagined. The silence deepens because the search improves. What once might have been excused as ignorance becomes harder to dismiss as instruments sharpen. This is why the listening efforts weigh so heavily on the Fermi paradox. They do not solve it by themselves, but they add an empirical edge. The problem is no longer only that logic seems to allow many civilizations. It is that actual telescopes, pointed with care and patience, continue to hear no confirmed reply. The gap between expectation and observation becomes a measured gap, one built from hours of listening, catalogues of stars, algorithms, repeated follow-up, and decades of careful filtering. A quiet sky might still hide minds, but it no longer hides them behind total observational poverty. Some part of the darkness has been sampled, and what returns is natural radio emission, interference, ambiguity, and absence. The act of listening, therefore, becomes part of the paradox itself. The more humanity learns how to hear, the more deliberate the silence appears. Not complete silence, not proven emptiness, but a silence specific enough to force the thought that either others are not there in detectable form, or they are present under conditions far stranger and less accessible than the early hopes of radio astronomy once imagined, beyond direct listening. Astronomers also search for evidence that intelligence may alter matter and energy on scales large enough to be noticed even without a message. This approach begins from a simple observation. A technological civilization need not speak in order to be seen. It may reveal itself through construction, energy use, waste heat, orbital changes, unusual patterns of starlight, or modifications to the environments around stars and planets. Nature produces many strange things, but it also follows regular physical rules. If a civilization grows large enough and uses enough energy, it may create signatures that depart from those natural expectations in detectable ways. The search for such signatures is often called the search for techno-signatures, a term broader than radio communication because it includes any observable consequence of technology. One of the most discussed examples is the Dyson sphere, though the original idea is better understood not as a solid shell enclosing a star, but as a swarm or collection of structures orbiting a star in order to capture a substantial fraction of its energy output. Such a system, if it existed, would alter the star's visible light and produce waste heat that would likely appear in infrared wavelengths. The idea matters not because astronomers expect stars to be literally hidden inside rigid shells, but because it offers a clear illustration of how large-scale engineering might become observable. A civilization does not need to send greetings across space. If it uses stellar energy at vast scale, thermodynamics requires that much of that energy eventually reappear as lower temperature radiation. In other words, great power use leaves heat behind. This makes infrared astronomy one of the natural tools for looking for advanced industry. Surveys have therefore examined stars and even entire galaxies for unusual excess infrared emission that might suggest large artificial energy harvesting systems. The results so far are negative in the confirmed sense. Strange objects certainly exist, but none has yet provided accepted evidence of extraterrestrial engineering. This absence matters because it narrows one class of expectation. If galaxy-spanning civilizations routinely build large energy-collecting structures, then some fraction of the sky should probably look different from what ordinary stellar populations produce. Yet the sky, when measured in this way, remains consistent with known natural processes. Individual stars have also drawn attention when their light behaves in unusual ways. The most famous case in recent years involves a star informally known as Tabby's star, whose brightness undergoes irregular dips that briefly lead some observers to imagine large artificial structures passing in front of it. As more data accumulate, the exotic explanation loses strength, and natural causes involving dust become more plausible, though the object remains scientifically interesting. This episode illustrates an important pattern in the search. Unusual data can provoke technological speculation, but careful follow-up usually favours natural explanations. The burden of proof remains high, as it should. A true techno-signature must not merely be strange. It must resist all ordinary astrophysical accounts and remain coherent under repeated observation. So far, no candidate has crossed that threshold. The same logic applies closer to home. If the solar system has ever been visited by extraterrestrial machines, some traces might remain in stable or protected environments. Airless bodies preserve surface features for long periods because they lack weather, flowing water, and active geology. The Moon is an obvious example. Its surface records impact across immense stretches of time. Asteroids also preserve ancient material, and certain orbital regions, such as some gravitationally stable points, could in principle host long-lived objects. These locations have inspired serious, if limited, discussion about whether an old probe might hide in a distant or inconspicuous part of the solar system. Searches have not found confirmed alien artifacts. This does not settle the issue completely, because the solar system is large and many small objects remain poorly mapped. Yet the absence of clear evidence again adds to the general quiet. If probes or outposts were common products of galactic civilization, the expectation of finding at least one artifact somewhere in nearby space would not feel unreasonable. Another possible technosignature lies in atmospheric chemistry. A planet with an atmosphere shaped by industry might contain gases that are unlikely to accumulate naturally in large amounts. On Earth, some manufactured compounds persist in the atmosphere and could, in principle, be detected by a distant civilization with advanced spectroscopy. This idea has become more interesting as telescopes improve in the study of exoplanet atmospheres. For now, most atmospheric observations remain limited, especially for small rocky planets, but the method points toward a future in which both biosignatures and technosignatures may be sought together. A living world might reveal oxygen, methane, or other combinations suggestive of biology. A technological world might reveal synthetic compounds, night-side illumination, or other energy-related anomalies. None of these indicators has yet been confirmed on another planet. But the possibility shows how indirect evidence may become increasingly important. The search therefore extends across a wide spectrum of scales. It includes radio beams, laser flashes, infrared excesses, unusual dimming patterns, atmospheric pollution, orbital engineering, and local artifacts. What unites these methods is the assumption that intelligence, once it alters its environment enough, becomes part of observational astronomy. It leaves footprints in light, heat, chemistry, or structure. So far, those footprints have not been confirmed. This does not prove that no civilization exists. It means only that the visible universe, at the levels examined, continues to behave as if nature alone is shaping what is seen. Stars flare, dust drifts, planets transit, gases absorb, and galaxies glow in ways explainable through ordinary astrophysics. The more this remains true, the more the Fermi paradox deepens. If nobody is transmitting, perhaps somebody has built. If nobody has built anything visible, perhaps somebody has changed a world. If no changed worlds are known, perhaps intelligence is either rare, subtle, brief, or turned inward in ways that leave little outward mark. Indirect searches therefore do not provide an escape from the paradox. They tighten it. They take away the comforting thought that maybe signals alone are missing while everything else might still be obvious. Instead, they reveal that the larger astronomical record also lacks confirmed signs of old and powerful civilizations. The sky continues to look natural, from nearby orbital space to distant galaxies. In that persistent normality, the silence acquires a broader meaning. It is not merely the absence of voices, it is also the absence of visible works. Distance is often presented as the most natural answer to the silence. Space is vast beyond ordinary intuition, and the stars are separated by intervals that make even the fastest current human spacecraft seem nearly motionless by comparison. Radio signals weaken as they spread. A message sent across dozens or hundreds of light years becomes harder to distinguish from background noise unless it is powerful, narrow, or intentionally aimed. Travel is slower still, even at the speed of light, which no object with mass can reach. Crossing the Milky Way would require about 100,000 years. From this perspective, the quiet of the galaxy can seem almost obvious. Perhaps civilizations are out there, but the distances between them are so extreme that contact becomes impractical, communication becomes faint, and the chance of any one world ever noticing another remains small. There is truth in this. Distance is a real constraint, not an illusion. Interstellar space imposes delay, isolation, energy cost, and risk. The problem begins when distance is treated not as a serious obstacle, which it certainly is, but as a complete explanation. The Fermi paradox becomes difficult precisely because distance alone does not account for the full age of the galaxy or for the cumulative effects of time. If the Milky Way were only a few million years old, then the argument from separation would carry much more force. Civilizations might simply not have had enough time to arise, develop, and spread, but the galaxy is old. Many stars and planetary systems long predate the Sun. This means the relevant question is not whether two civilizations alive at the same moment can easily converse across the disk. The relevant question is why, over billions of years, no civilization appears to have crossed enough of the intervening space to leave clear traces. Once that deeper timescale is acknowledged, distance begins to shrink as a final answer. It remains difficult, but it no longer feels decisive. Signals also complicate the objection in an unexpected way. Communication over long distances is indeed hard, especially if signals are weak, unfocused, or rare. Yet a civilization that wants to be noticed might choose highly conspicuous methods, powerful beacons, repeated transmissions, or narrow-band signals aimed at promising stars. Humanity itself has long recognized certain frequencies as potentially useful for such purposes, especially regions of the radio spectrum where natural background noise is relatively low. This does not mean alien societies would share human preferences, but it does mean that distance does not eliminate the possibility of communication. It only narrows the kinds of communication likely to succeed. A focused transmitter and a patient timescale can still bridge very large separations. Moreover, the paradox is not limited to messages. As earlier reasoning shows, it also concerns physical spread, durable artifacts, and large-scale engineering, all of which can accumulate over deep time. Distance slows these things. It does not make them impossible. Another weakness in the distance argument appears when the galaxy is imagined too much as a smooth and empty void. In reality, stars occupy neighborhoods. The Sun is not isolated in a featureless desert. It has nearby stellar neighbors, some with planets, some perhaps with small bodies rich in useful material. Similar local neighborhoods exist throughout the Milky Way. A civilization need not cross the entire galaxy in one leap. It can move to the nearest system, then the next, with each step taking place over generations, centuries, or longer. This process may be slow enough to feel hopeless on a human timescale, but the galaxy is not measured in human patience. It is measured in millions and billions of years. A civilization that survives and continues even modestly could, in principle, cross astonishing distances one local move at a time. Distance, therefore, changes from a wall into a rate limiter. It determines how fast spread happens, not whether spread can ever happen. That distinction matters. Some defenders of the distance explanation may reply that civilizations need not expand at all. This is true. No law of nature requires outward movement. A society may choose stability, inward development, virtual existence, or local ecological balance. Yet the paradox becomes difficult because it asks not whether one civilization might remain homebound, but why all of them would do so across the entire history of the galaxy. Diversity of motives is one of the most ordinary facts about intelligent behavior on Earth. Exploration, exile, trade, curiosity, ambition, fear, and accident all move populations and technologies. It is therefore difficult to assume that every extraterrestrial civilization, if many exist, would independently choose permanent stillness. Distance may discourage expansion, but for it to fully explain the silence, it must combine with a universal lack of sustained outward activity. That is a stronger claim than the simple statement that space is large. There is also a subtle observational point. Distance affects what can be seen, but not in the same way for all kinds of evidence. A faint local radio leakage may disappear quickly into noise. A massive engineering project around a star may remain visible much farther away through its effect on light and heat. A probe left in a stable orbit within the solar system would not be hidden by interstellar separation at all. Thus, when distance is invoked as a general answer, it tends to blur together very different classes of phenomenon. It is a good explanation for why casual conversation between worlds may be rare. It is a weaker explanation for why no unmistakable traces of long-term technological activity have been confirmed anywhere within observational reach. This is why distance functions best as part of the paradox rather than its solution. It explains why direct contact might be uncommon, delayed, or difficult. It explains why the sky may not be filled with obvious chatter. It does not adequately explain why a galaxy so old, so populated with stars and worlds, and so open to gradual spread still appears free of confirmed artificial marks. The silence remains too broad. It covers radio, visible structures, infrared anomalies, and nearby artifacts alike. That breadth pushes thought beyond mere size. The emptiness between stars is real, but it may not be the deepest problem. The deeper problem may lie with the beings who might try to cross it, with how often they begin, how often they endure, how they use technology, and whether they remain visible for long. In this sense, distance is the first objection because it feels intuitive, almost comforting. It makes the quiet seem like a mechanical consequence of scale. Yet once examined in the full context of galactic history, it loses some of that comfort. Space is large, but time is larger still. Over billions of years, even the slow can become far-reaching. When that is remembered, the silence grows heavy again, no longer softened by emptiness alone. One family of explanations accepts the possibility that civilizations may be present while remaining unseen. In these views, the silence does not arise because intelligence is absent, but because it is hidden, restrained, or intentionally difficult to detect. Among the best-known versions is the zoo hypothesis, proposed in formal form during the 1970s. The central idea is that advanced civilizations know about younger worlds such as Earth, and choose not to interfere. Humanity is then imagined not as alone, but as part of a monitored environment, observed from a distance much as humans observe wildlife reserves, or avoid direct contact with isolated tribes. The appeal of the idea lies partly in its simplicity. It allows the galaxy to contain many civilizations while explaining why no clear signal arrives and no public encounter occurs. It also feels psychologically familiar. Humans already recognize situations in which greater power is paired with restraint, curiosity, and non-intervention. A technologically older society might decide that contact would distort the natural development of younger species. It might choose secrecy out of ethics, caution, or indifference. On the surface, this seems more plausible than fantasies of constant galactic diplomacy or universal conquest. The hypothesis gains further appeal because it does not require alien life to be rare. It preserves a populated cosmos while moving the explanation for silence into the behavior of advanced beings. Yet the closer the idea is examined, the more difficult it becomes to sustain as a complete answer. Its main weakness is coordination. For Earth to remain effectively hidden from open contact across billions of years, every relevant civilization, or at least every civilization capable of reaching or observing this region, must independently maintain the same policy. Not just one civilization, not just a majority. All of them. No dissenter can openly transmit. No careless probe can wander into obvious view. No faction can break the pattern. No civilization in the long history of the Milky Way can choose curiosity over restraint in a way detectable to us. This requirement becomes especially severe once one remembers that the galaxy may contain many stars older than the Sun by billions of years. Even if only a small fraction host advanced intelligence, the number of independent histories could still be substantial. Expecting perfect consistency across those histories strains credibility. Human beings cannot sustain universal agreement even on one planet, across one species, within a very short historical span. Agreements fail, institutions fragment, and individuals act outside common policy. To imagine a galaxy in which countless independent intelligences all preserve an invisible quarantine indefinitely is to ask for a degree of coordination much greater than anything known from human social behavior. The problem becomes sharper when accidents are considered. Perfect secrecy is hard even for deliberate systems. Artifacts fail, signals leak, missions go wrong, and observers make mistakes. Over millions or billions of years, even low probabilities accumulate. One broken machine, one poorly concealed observation post, one exploratory act by a marginal group, one abandoned structure in a visible orbit might be enough to reveal the presence of others. The continued absence of confirmed evidence suggests either extraordinary discipline or the weakness of the explanation itself. The zoo hypothesis remains possible in a strict sense, because concealment cannot be disproved absolutely. But as a universal solution to the Fermi paradox, it demands more than it first appears. It demands not only hidden civilizations, but hidden civilizations that remain successfully hidden in every relevant case across cosmic time. There is also an observational issue. A non-intervention policy may explain the lack of open contact with Earth, but it does less well at explaining the lack of visible activity elsewhere. Even if advanced civilizations avoid direct interference with young planets, they might still reshape their own systems, build observatories, harvest energy, or move through the galaxy in ways visible from afar. To save the hypothesis, one must often add a second assumption, that they also conceal all major external works. The solution then grows more elaborate. Silence is no longer simply the result of restraint. It becomes the result of universal restraint combined with universal concealment. That may be possible, but every added layer reduces elegance. Another hidden civilization idea is less benevolent and more strategic. In this version, silence exists because revealing one's presence is dangerous. Civilizations do not stay quiet out of kindness toward younger worlds, but out of fear of other civilizations whose motives are unknown. From a distance, intentions cannot easily be verified. Even if a signal is received, the sender's future capabilities, morality, and long-term aims remain uncertain. Since interstellar communication is slow, negotiation is difficult, and misunderstanding may persist for centuries. Under such conditions, one can imagine a galaxy in which silence is treated as safety. This broad concept is sometimes associated with the phrase dark forest, though the phrase itself comes from fiction rather than formal astrophysical theory. The image is memorable because it casts the galaxy as a place where every civilization moves carefully, avoids drawing attention, and listens more than it speaks. Such an idea has emotional force because it turns absence into presence. The sky sounds empty, not because nobody exists, but because everyone is afraid. It also carries a hard strategic logic. If uncertainty is large enough and the stakes are total survival, then even a small probability of danger may encourage secrecy. Still, as a full explanation, the dark forest view faces serious problems. The first is that it again assumes an almost universal behavioral pattern. Every civilization must conclude that silence is best. Everyone must follow that conclusion consistently enough to suppress conspicuous broadcasting. But the histories, psychologies, and risk tolerances of independent species may vary enormously. Some may be cautious, some may be reckless, some may be curious enough to transmit anyway. Others may lack the capacity to perceive the strategic risk at all. Across billions of years, the appearance of at least some open broadcasters seems difficult to rule out. The second problem concerns enforcement. Fear alone may explain silence, but it does not easily explain the absence of visible consequences if hostile civilizations actively destroy those who broadcast. Interstellar attack is not obviously impossible, but it is technologically demanding, delayed by light speed, and hard to execute with certainty over great distances. If the galaxy were shaped by repeated episodes of predatory silencing, clearer traces might be expected in disrupted systems or large-scale anomalies. None has been confirmed. The hidden civilization class of explanations therefore occupies an intriguing but unstable position. It preserves a living galaxy while accounting for quiet through behavior rather than absence. Yet to carry the full paradox, it usually needs universal motives, near-perfect discipline, or unobserved strategic dynamics operating flawlessly across cosmic history. The more the idea is extended to explain all silence, the more those assumptions accumulate. What begins as an elegant possibility becomes a demanding one. Hidden civilizations may exist. Some may choose non-interference, some may choose caution, but as a total answer, concealment remains difficult because the galaxy is not just wide, it is old, diverse, and full of opportunities for one exception to become visible. The paradox endures partly because no such exception has yet been confirmed. Another family of explanations turns away from hidden civilizations and looks instead at the conditions required for complex life itself. In this view, the galaxy may contain many stars and many planets, yet the path from simple matter to durable intelligence may still be extraordinarily narrow. This is often called the rare Earth perspective, though the name can be misleading if taken to mean that planets like Earth are literally unique. The more careful claim is that while rocky planets in temperate orbits may be common, the full combination of conditions that allows long biological continuity and the eventual rise of technological intelligence may be uncommon or even exceptionally rare. The force of this argument lies in accumulation. Each individual requirement may seem modest. Together, they may sharply reduce the number of worlds where complexity has enough time and stability to emerge. The first filters may begin with the star. Not every star offers a gentle and long-lasting environment. Very massive stars burn hot and die quickly, giving complex evolution little time. Small red dwarf stars are far longer lived and very numerous, but many are active in ways that may complicate habitability. Their habitable zones lie close in, where planets may become tidally locked, and where intense flares can erode atmospheres or stress surface chemistry. None of this proves such systems are lifeless, but it reminds observers that not every habitable zone is equally benign. A world may sit at the right distance for liquid water and still face conditions that make long biological development difficult. Then comes the planet itself. Earth is not only a rocky body with water, it has a substantial atmosphere, a magnetic field generated by a dynamic interior, active geology, and long-term cycling between rock, air, and ocean. Plate tectonics helps regulate carbon dioxide over geological time, moderating climate through feedback between weathering, burial, volcanism, and atmospheric composition. Without such regulation, a planet may drift toward deep freeze or runaway heat. Mars and Venus stand as nearby reminders that rocky planets can diverge dramatically even within one solar system. Mars appears to lose much of its early atmosphere and surface water as its interior cools and its magnetic shielding weakens. Venus becomes a furnace under a dense atmosphere dominated by carbon dioxide. Earth, by contrast, remains habitable over billions of years despite major changes. This stability may not be guaranteed elsewhere. The Moon also enters the discussion. Earth's large moon stabilizes the tilt of the planet's rotation axis, limiting chaotic swings that could otherwise drive extreme long-term climate shifts. The exact importance of this effect remains debated, because some models suggest Earth might still retain relative stability without such a moon, though perhaps less reliably. Even so, the Earth-Moon system is not obviously a universal planetary arrangement. If axial stability matters, then many apparently suitable planets may still prove less favourable for long biological continuity. Larger architectural features of the solar system may matter as well. Jupiter is sometimes imagined as a shield that protects Earth from impacts, though this simple picture is now treated more cautiously, since giant planets can both deflect and redirect bodies in ways that increase or decrease impact rates depending on circumstance. Even so, the arrangement of planets in a system influences orbital stability, delivery of water, bombardment history, and the persistence of climates over immense spans. Habitability may therefore depend not only on one world in one orbit, but on the broader dynamical design of the system around it. The rare Earth line of thought then deepens further by distinguishing simple life from complex life. Microbial organisms may perhaps arise under a wider range of conditions, but complex multicellular life may require long periods of environmental stability, sufficient oxygenation, nutrient cycling, and the avoidance of repeated sterilizing catastrophes. On Earth, simple life appears early, yet complex animals arrive very late. For billions of years, life remains microbial. This suggests that the step from chemistry to cells may be easier than the step from cells to large bodies, nervous systems, and eventually intelligence. If so, the galaxy could host many living worlds while still remaining nearly silent in technological terms. The problem may not be the origin of life, but the rarity of the later transitions. This is where the idea of a great filter begins to take shape. A great filter is not a single named event, but any barrier so difficult that very few lineages pass it. The filter could lie behind humanity, meaning the origin of life, the emergence of complex cells, multicellularity, or intelligence itself may be extraordinarily rare achievements already completed on Earth. In that case, the silence of the galaxy would be reassuring in one sense. It would imply that humanity has already passed the hardest barriers. The alternative is darker. The filter could lie ahead. Civilizations may commonly arise to the point of technology, and then fail before becoming long-lived and visible across space. That failure could come through ecological breakdown, war, uncontrolled technological risk, exhaustion of habitable conditions, loss of coordination, or causes not yet imagined. The emotional weight of the great filter idea comes from this uncertainty about location. A silent galaxy may mean rare success or repeated collapse. Rare Earth explanations and great filter reasoning are not identical, but they overlap strongly. Both suggest that the transition from matter to enduring civilization is narrower than the abundance of stars and planets first implies. What makes these ideas scientifically serious is that they do not rely on hidden motives or speculative cosmic violence. They rely instead on known fragility. Earth's habitability depends on interacting systems that are complex and contingent. Evolution does not move toward intelligence by any obvious necessity. Civilizations acquire dangerous powers quickly. At every stage, there may be branching failures. The paradox then changes character. The question is no longer mainly why nobody has visited. It becomes why the chain from star formation to detectable civilization might be so easy to begin and so hard to complete. If that chain contains only a few very narrow gates, then even a galaxy rich in worlds may remain mostly quiet. Yet this answer, while plausible, does not entirely calm the puzzle. It relocates it. One still wants to know which steps are truly rare, how rare they are, and whether humanity is unusual because it has already crossed them, or because it is approaching one it cannot yet see. The rare Earth and great filter views therefore do not remove the tension. They gather it inward, toward biology, planetary history, and survival. In doing so, they make the silence of space feel less like a distant astronomical curiosity and more like a mirror held up to the long and fragile sequence that has led from ancient stars to human thought. At the innermost level of the paradox, the question is no longer about stars, planets, signals, or machines alone. It becomes a question about the nature of intelligence and whether intelligence tends, by its own structure, to produce conditions that make long survival difficult. This is the most unsettling possibility because it does not depend on rare chemistry or hidden civilizations. It depends on a recurring instability built into the passage from thought to power. A species may evolve awareness, memory, cooperation, and technical skill because those traits help it survive in a local environment. Yet once those abilities begin to compound, they can quickly exceed the social, ethical, and ecological systems that first support them. Intelligence then ceases to be only adaptive. It becomes transformative. It changes landscapes, climates, energy flows, food systems, communications, and weapons. It creates abundance and fragility at the same time. If this pattern is common, then the galaxy may not be empty because life fails to arise. It may be quiet because civilizations repeatedly enter phases of self-generated risk that few successfully cross. On Earth, this possibility is visible not as a final verdict, but as an active tension. Human beings gain control over fire, agriculture, metallurgy, engines, electricity, chemistry, computation, nuclear reactions, genetics, and machine intelligence within a short fraction of the planet's biological history. Each gain expands possibility. Each also creates new dependencies and new pathways for harm. Industrial society increases life expectancy, literacy, and technical reach. Yet it also alters atmospheric composition, ocean chemistry, forests, rivers, and biodiversity on a planetary scale. Nuclear science reveals the structure of matter in the age of stars, while also placing destructive force in the hands of political systems shaped by rivalry and fear. Networks connect billions of minds, yet they also accelerate misinformation, surveillance, and social fragmentation. None of these outcomes proves that intelligence is doomed. They show that intelligence changes the environment faster than the slower processes of biological evolution can respond. Cultural adaptation must bear the entire burden, and cultural adaptation is uneven, reversible, and often driven by short-term incentives rather than long-term stability. This may be the central difficulty. A technological civilization can become globally powerful before it becomes globally wise. It can master external systems while remaining divided internally. It can generate tools capable of reshaping planets before it develops institutions robust enough to govern those tools safely across generations. the gap between capability and restraint may be the dangerous interval. If so, the great filter ahead, if there is one, need not be a single disaster. It may be an extended phase in which intelligence must learn to coordinate at scales equal to the powers it has unlocked. Failure may come through sudden war, but it may also come through slower erosion, through the accumulation of many moderate instabilities that together undermine resilience. Climate stress, ecosystem loss, technological concentration, economic fragility, engineered pathogens, autonomous weapons, and irreversible environmental change do not need to arrive as one dramatic event. They may simply narrow the room for error until one shock becomes decisive. Another possibility is that civilizations survive but cease to radiate outward ambition. The common image of long-term intelligence often assumes expansion, grand engineering, and growing visibility. Yet an enduring civilization might instead optimize for stability, efficiency, and low external signature. It may reduce waste heat, communicate narrowly, build inward rather than outward, and conserve rather than expand. Such a society could persist for very long periods while remaining difficult to notice. This would soften the implication that silence means death, but it would not remove the challenge. Even inward civilizations must still pass through the unstable earlier phase in which technology rises faster than wisdom. The narrow question remains whether many societies do so successfully. There is also the problem of motivation across deep time. Civilizations are not fixed entities. Values change, institutions dissolve, descendants diverge, and purposes shift. A species that survives for millions of years may no longer resemble its origin in psychology or behavior. It may merge with machines, inhabit artificial environments, spread into many branches, or relinquish many outward-facing projects. Long survival could therefore produce invisibility through transformation rather than extinction. Yet again, the filter would not disappear. It would simply move to the challenge of surviving long enough to transform. The silence then reflects either collapse, concealment, or change. What makes the innermost level of the paradox so difficult is that all these possibilities point back toward the same vulnerable threshold. Intelligence must live with the consequences of its own success. It solves problems by increasing control over matter and energy. But every increase in control widens the scale of mistakes. A fire can warm a shelter or burn a forest. A chemical industry can feed billions or poison rivers and air. Computation can coordinate systems or destabilize them through speed and opacity. Biological understanding can heal or harm. The very tools that might enable a civilization to reach the stars are the tools that may first test whether it can govern itself. In this sense, the silence of space may not be merely an astronomical fact. It may be an indicator of how hard it is for knowledge and power to remain aligned with continuity. The outer galaxy still shines with abundance. The inner logic, however, may be unforgiving. Many worlds may form. Some may host life. A smaller number may produce intelligence. A smaller number still may reach technology. The final reduction may come not because civilizations cannot imagine the stars, but because they struggle to survive the period in which they first become capable of acting on that imagination. Humanity stands inside that uncertainty now. It does not yet know whether technological intelligence typically destroys itself, matures beyond danger, becomes subtle and hard to detect, or simply appears so rarely that Earth is one of the few places where the question can be asked. The Fermi paradox remains unresolved because all these possibilities are still open. Yet the silence acquires its deepest force when seen not as a distant riddle alone, but as a warning carried by absence. The universe may be quiet for reasons rooted not in the emptiness between stars, but in the difficulty of remaining a civilization long enough to cross it. The galaxy remains overhead in its usual stillness, broad and ancient, carrying more stars than any human mind can comfortably imagine, and more time than any civilization has yet learned to inhabit. Through each outward layer of the question, the same contrast remains. The Milky Way appears full of opportunity, full of planets, chemistry, energy, and long histories. Yet when the search turns towards signs of intention, the record remains quiet. No confirmed signal, no visible work, no artifact close at hand has yet settled the matter. The silence therefore does not feel simple, it feels shaped. It suggests either that the steps from matter to mind are far narrower than they first appear, or that minds do emerge and then pass through intervals too brief, too fragile, or too hidden to leave a lasting mark that another world can easily see. In that uncertainty, the paradox rests not as a solved problem, but as a patient one. It waits in the background of astronomy, biology, and the future of civilization itself. Humanity remains at the beginning of its own detectable moment, old enough to ask the question, and still too young to know what kind of answer its own history will become. The stars do not yet reply. They remain as they have always seemed from Earth, bright, distant, and silent in the human sense, carrying only natural light across the dark. Within that calm, the question stays open. The galaxy may be empty of other civilizations, or it may be full of histories that never overlap, never endure, or never choose to announce themselves. Until stronger evidence appears, the silence remains both a mystery and a measure of how little is yet known about life, intelligence, and survival on cosmic scales.